Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. People use two ears to hear. In this video, we'll learn all about this binaural hearing, the means by which we localize sound sources in our environment.
So let's get started. The practice of using two ears to hear is referred to as binaural hearing. And if you look through older documents, you might hear this referred to as stereophonic hearing. So many psychoacoustic phenomena actually rely on both ears to function, and data shows that the loss of hearing in one ear can dramatically reduce the capabilities for us to hear and synthesize sound, which confirms the significance of binaural hearing. Source localization is the first binaural function that we'll focus on. It's one of the most primordial binaural functions. The sound that one ear hears is different than the sound that the other ear hears, due to the relative positioning of the ears with respect to the sound source. So we have our sound source here located in spherical coordinates, radial distance r, azimuthal angle phi, and elevation angle theta. Our brain uses these differences of what's heard between ears to locate sound sources. There are two primary source localization mechanisms that thus result in binaural hearing. The first is interaural time difference. So for a source in the azimuthal plane, the difference in time of arrival for the wave to arrive at the different ears is the interaural time difference, the ITD. So we have here in the schematic on the right, beta, which is an angle of arrival for the incident wave that we're trying to localize. We also have here the variable r, which is the average radius of the head from the center of the head to the ear canals, which is around 90 millimeters. So it's not the whole radius of the head, instead it's only the distance from the center of the head to the ear canal. We see here the difference of travel for the wave to the left ear than to the right. In this example, it's this distance r beta plus r sine beta. When we divide this distance by the sound speed, we get the ITD, the interaural time difference. This presumes that the head is a rigid sphere, and this is fairly accurate for the lower frequencies for which ITD is useful. The greatest angle of arrival, of course, is 90 degrees. And if we substitute this back in to our equation for ITD, that means that the greatest ITD is around 674 microseconds. This doesn't yet tell us what frequencies we can resolve by ITD, on the other hand. To resolve the location, we must resolve distinct points of phase for the incident wave. Take, for instance, a low-frequency wave that's shown in the schematic at the right. At time t0, one point of constant phase arrives at the right ear. At time t1, that same point of phase arrives at the left ear. There are no other possibilities for which this could have occurred, so our brain recognizes this sound came from the right. Now, let's consider a high-frequency case. A point of phase arrives at the right ear. At time t1, that same point of phase arrives at the left, but it's not actually the original point of phase. Only at time t2 does the original point of phase arrive to the left ear. As a result, spatial aliasing like this prevents us from using ITD-based localization at high frequencies because we are unable to resolve the exact distinct point of phase from one ear to the next. If we multiply both sides of the ITD equation by 2 pi times frequency, we would have phase on both sides of the equation. So we have the phase of the ITD is equal to 2 pi f times r, the radius of the head, multiplied by beta plus sine beta, all of which is divided by c. Given that the maximum phase difference between ears can only be pi radians before spatial aliasing occurs, we find then that the maximum frequency for which ITDs are distinct is 741 Hz. In general, though, the ITD alone is insufficient to localize sources more accurate than around 5 degrees azimuthal resolution. We need other mechanisms to assist us in this effort. The interaural level difference, the ILD, is what we use at higher frequencies than what ITD-based localization provides. The interaural level difference occurs due to diffraction around the head, not due to additional distance traveled. We see here at low frequencies, little diffraction occurs, so the left ear largely hears the same level that the right ear does. But at higher frequencies, there's much more significant diffraction and blocking of sound around the head. This leads to shadows and very large level differences that we use to localize sounds with mid to higher frequencies. To summarize what we've learned, binaural hearing is central to sound source localization. Together, the interaural time differences due to time of arrival differences and the interaural level differences due to wave diffraction, these together result in the means for many animals, including us, to localize sounds. It's spatial aliasing that then prevents us from using ITDs at higher frequencies, although on the other hand, the ILD at higher frequencies is very substantial than the ILD at low frequencies.
That's it for this video. In the next video, we'll learn more nuances about the frequency filtering we use in our binaural hearing.